So we're going to put one more little tool in our pocket before we start solving exponential and logarithmic equations. We're going to put the change of base formula in our pocket. And the idea is, again, that we want to justify the formula so that we don't think it's magical. So the claim is that if we have log base b of x, that we can change the base and come up with an equivalent expression. And we can do it by taking log base a of x, where x is coming from there, and dividing it by log base a of b. So this is a change of base formula. For any logarithm base b, we can convert it into an expression base a by taking log base b of x and rewriting it as log base a of x divided by log base a of b. And an easy way to justify this is to take log base b of x and give it a name, similar to what we did when we were deriving the properties for logarithms, the power, the quotient, and the product properties. So just give that logarithm a name, and then recognize that the logarithm is an exponent, so that means that y is now an exponent. What exponent is y? Y is the exponent you raise b to get x. So we can rewrite this in exponential form as b to the y must equal x. And then once I do that, I can take log base a of both sides. Log base a of both sides, where a is any legitimate base. Log base a of both sides. So we're going to take the left hand side and input it into log base a, which means we need to take the right hand side and do the same thing. And then remember, from the log properties, we had the power property that says if we have b to the y inside log base a, that the y can be brought down front into a product position. So we can rewrite this as y times log base a of b equals log base a of x, and then just divide both sides by log base a of b, divide both sides by log base a of b. Log base a of b divided by log base a of b is just equal to 1, and we get y times 1 is just equal to y, so we get y equals log base a of x divided by log base a of b. But if y is equal to log base b of x and y is equal to log base a of x divided by log base a of b, then these two things, log base b of x and this ratio here, they must be the same, which establishes the result that we wanted. And the primary importance of this particular property is if we are working with a logarithm base anything but 10 or e, then we don't have a key on our calculator to approximate it. So there's no way for us to do log base 7 on a calculator, but our calculator does have a log base 10 key, and it does have a natural logarithm key. In a lot of the modern computer algebra systems, we don't need to do a change of base to solve or approximate a logarithm, because the computer algebra systems will have the capacity to deal with multiple logarithms. So here's an application of the change of base formula. So we want to evaluate log base 7 of 60, and we want to do it using a calculator. And again, the issue is going to be that the calculator doesn't have a key for base 7 logarithms. So we can just use the change of base formula, and we can use log base 10, for example. And the change of base formula says that if you have log base b of x, then you can do log base a, and the x is going to go in there, and the b is going to slide down into this position. So changing from log base 7 to log base 10, we'll just slip the 60 in here and the 7 in here. And I could just as easily have done this with the natural logarithm, because the base doesn't matter on the change of base formula. It doesn't matter what base a is, as long as it's a legit base. So I could use log base e, which is the natural logarithm, and put a 60 and a 7 here. And if I take those and pop them into a calculator right here, so I have my log button right here. So if I do log of 60, and then I divide that by log of 7 and approximate that ratio, it's about 2.1-ish. I could just as easily have used the ln, or the natural log key on the calculator. I could have said natural log of 60 divided by natural log of 7, and if I hit enter, I'm going to get the same approximation because the base doesn't matter. If I'm using something like GeoGebra, which is a computer algebra system, GeoGebra, let's see if it fires up fast. I should have already had it loaded, but I didn't decide until I was into the video that I wanted to pull this up in GeoGebra. Hence our waiting for the program to load at this point. So in GeoGebra, you can graph in another base. So let me see if I can get this up where the input bar is more visible. We can use other bases, like in the input bar, equals, if I want to do log base 7, I hit the underscore button and put 7. So if you do underscore and then the base that you want, you can see that it's slotted that base into the correct position. So if I'm going into my view, my computer algebra system, if I wanted to know log base 7, I could go underscore 7 of 60. You can see it automatically did a change of base on it. And if I click that little circle, it's going to throw the approximation over here into the window for me. And again, like we were talking about the other day, you can get a better approximation by going into options, rounding, and increasing the number of decimal places. So here's the approximation being displayed here, but you can see it actually applied the change of base formula by using natural logarithms.